Good morning, everyone. Welcome back. We're going to be discussing about combinatorial logic and CMOS circuits with an example of a NAND gate, how we can develop a circuit using a PMOS and NMOS, as well as an example of layout, physical layout of the NAND gate. All right. So what's in combinatorial logic? We have inputs, okay, and the idea is to get the outputs. So combinatorial logic is a function. One can think of a function which takes Boolean input values and produces the output, which can be either logic 1 or logic 0 depending upon the inputs, or in other words, output as well as inputs belongs to set 0 and 1. All right, so that's the job of the combinatorial logic. Now, when we look at it, the output, it can go either 1 or 0. So that gives us an important clue that our combinatorial logic circuit can be divided in two parts. One part can pull the value to 1 or a pull-up circuit, okay, which can pull the value of the output to VDD, okay, or logic level 1. The pull-up is connected to VDD, okay. And then second part, we can think of a pull-down circuit, which can pull the value of the output to 0, logic level 0, okay. Now, what if we connect these pull-up and pull-down network? Then we can get desired output, which can go either logic level 1 or logic level 0 depending upon the inputs. Okay, so that's a very important fact, that any combinatorial logic can be divided in two parts, pull-up network and pull-down network. And then these two pull-up and pull-down networks can be joined together, connected together to produce the desired output. That's good. Now, let's review it. So pull-up network's job is to pull the value or output to logic level 1, and pull-down network's job is to pull the output value to logic level 0. Good. So basic concept is clear here. Now, let's look at it. What we have, NMOS and PMOS. So here I'm showing first the PMOS example for a reason which we'll come to know later. So we have a PMOS, and what if we connect the gate of the PMOS to ground and one of the terminal to VDD, and we take the output from another terminal, and we find that this combination produces a strong 1 when we connect the gate to ground and one of the terminal to VDD, a strong 1. Other combination, one can argue that, oh, I want to connect to VDD gate and then other to ground. Those are all produces, other combination produces the weaker 1 or 0 depending upon the configuration. So the best configuration is chosen to produce a strong 1 is to connect the PMOS gate to ground and one of the terminal to VDD. Okay, so that produces strong 1, which means that indicates that circuit PMOS we could use for constructing the pull-up network. Okay, all right. So this PMOS or this circuit pulls the output to 1, a strong 1. We can formalize it. Let's say input is I1 and output we can denote it as a function f pull up. Okay, so when I1 tends to 0, f pull up tends to 1, a stronger 1. Okay, remember this equation. Good. Now let's look at the NMOS. Okay, NMOS. So what does the NMOS do, right? You all know what does the NMOS do. Electrons flow through the channel, right? And the current flows from between two terminals, okay, depending upon the gate voltage. Now, if the gate is connected to VDD, right, gate is connected to VDD, so what's going to happen? That whatever charge was accumulated at here will flow down to the ground, or electrons will flow down to the ground, and this will construct a conducting path. Or in other words, the output is pulled down to logic level 0. Good. And this produces a strong 0. So that tells us that we could use NMOS for constructing the pull down network. Let's formalize it. Let's call it I1, and output is F of DN, means pull down network. And when I1 tends to 1, then F, or output of pull down network, tends to 0, and it's a stronger 0. That's good. So what we have formalized or discussed, that we could use PMOS for producing a stronger 1 for pull-up network, and we could use NMOS for producing a stronger 0, or in other words, constructing the pull-down network. Good. Now let's look at, right, we can have for each input, here let's say we have n inputs, I1, I2, I3, I4 up to In. So we could have n PMOS and n number of NMOS circuits, okay? And when each input will tends to 0, then the output will tends to 1, a stronger 1, and we can call it the pull-up network output. Similarly, if the inputs tends to 1, then output tends to 0, a stronger 0, and we could call it pull-down network. Output tends to 0. So two important concepts we formalized here. Pull-up network, we could use PMOS for producing a stronger 1. Pull-down network, we could use NMOS for producing a stronger 0. The gate of the PMOS, we could connect to the ground when we want to produce 1 at the output. And we could connect the gate to VDD of NMOS, for NMOS when we want to produce the stronger 0 output for the pull-down network. Good. Now let's look at the one example, very simple example of a NAND gate. Okay, we have two inputs, I1 and I2, and it produces an output which is in NAND logic. Okay, or in other words, I1 ANDed with I2 and inverted NAND logic. If we put it on a truth table, how does it look like? That I1, I2 and F, and we can put all the combination. We have 4 combinations here. So if you look at it here, when I1 and I2 both are 1, then only output F is 0. Otherwise it is 1. Okay. So once again, only when I1 and I2 is 1, output is 0. Otherwise, doesn't matter whether either of the I1 and I2 is 0 or one of the I1 and I2 is 1, output should be 1 for the NAND gate. All right, good. So idea is that with this help of the logic function, right, truth table, can we use, how can we use NMOS and PMOS, or concept of the pull up and pull down, which we just discussed, to construct the circuit, okay, of the NAND gate. So for the PMOS, we know that if we connect the gate of the PMOS to ground, it produces the stronger one. Okay, we just discussed, we're just putting it again here to remind. Okay, so we have here two inputs and we have two PMOS. Good. Now, what if we connect these two PMOS in parallel? Okay, so this is a parallel structure where uh, uh, each PMOS, one of the terminal is connected to VDD and another terminal, both are connected together. This is a parallel combination. Okay, now let's see what happens. We can call it F PUN because idea is to construct the pull-up network. So what if we connect I1 to ground? So what's going to happen that the holes will flow through the channel and will reach to the another terminal. Okay, so this level of the output at the another terminal of the I1 PMOS, okay, that will reach to logic level 1 or a stronger one. Good. Now let's look at if we connect gate of the I2 PMOS, or input is I2, what's going to happen? So whatever charge is accumulated here, that will find a conducting path via holes conduction, the concept of the PMOS, right? You all are aware of holes conduct in PMOS and electrons in NMOS, okay, opposite nature. And that will reach, and the terminal, another terminal of I2 PMOS will have logic level 1, or as we discussed, it produces a stronger one. So no matter whether we have I2 or I1 or both of them are connected to ground, tends to 0, it will produce a stronger one at the output. Or we can call it like output of a pull-up network will be stronger one when either of I1 and I2 PMOS gate is connected to ground. Good. Okay. So remember the OR logic. Okay. So PMOS are connected in OR logic for pull-up network. F P1 is equal to I1 or I2. Remember this equation. Good. Now let's look at the NMOS. So we have discussed about the NMOS just a few minutes back. If we connect the gate of the NMOS with the VDD, electrons find the conducting path and they pull down the one of the terminals higher voltage to ground. Okay, and that terminal we could call it the we could take the output, okay, which is pulled down to ground. Good. We have formalized the equation. When I1 or I2, if they tend to 1, function f or output tends to 0, and which is a stronger 0. Now let's try to find a connection. Okay, so what if we connect NMOS in series? Okay, and we connect both of the NMOS gates to VDD. What's going to happen now? That the electrons will find the connecting path to the ground, and they will pull down the output output level to 0, and we could call it output of the pull down network. The condition here is that both of the gate has to be connected to VDD. What happens if, let's say, one of the gate you have connected to VDD and you have not connected this one? Then charge will be accumulated here and it will not be a stronger 0 at PDN, okay, or output. So in this structure, when the NMOS are connected in series, the gates of the both NMOS I1 and I2 has to be connected to VDD to produce a stronger 0 at the output. Okay. All right. So this we can call it AND. This is the AND logic. Okay. So remember, NMOS we connect in series and it produces a AND logic. Okay. PMOS or OR logic and NMOS AND logic. Good. Or in other words, we can call it pull up network is I1 or I2 and pull down network is I1 and I2 for this NAND gate logic. Okay. Good. So this is just to formalize and remind ourselves what we just discussed. I1 or I2, when they tends to 0, pull up network will produce a stronger one, and when I1 and I2 both are in series and tends to 1, the pull down network output will produce a stronger 0. Or in other words, pull up network, we should keep in mind thinking about OR gate or OR logic for connecting the PMOS, and for pull down network we should be thinking about AND logic or connecting the NMOS in series. Good. So let's go back to the very first diagram what we discussed about the combinatorial logic. We can divide up in two networks, pull up or pull down, and we can connect them together to get the desired output F. Now since we established the fact that NMOS are connected in series and PMOS are connected in parallel, okay, so for pull up network and NMOS for pull down network, let's see what we can do now. Okay, what if we connect? This is what we discussed. We connect the pull up and pull down network together. Here also we connect pull up and pull down network together. Okay, and we get the desired output of the combo logic F as an output, and that output will give us the NAND logic gate output. For example, this circuit is the NAND, 2-input NAND gate. Okay, and we can further simplify the diagram, circuit diagram for 2-input NAND gate. Good. Now let's discuss about what if we have n inputs. So this particular circuit we can keep connecting the n number of NMOS in parallel and n number of let's discuss about the multi-input NAND gates. So when we have more than 2 inputs, okay, so we could connect PMOS, n number of PMOSs in parallel and n number of NMOS in series. Okay, And at the intersection of these two networks, pull-up network and pull-down network, we can get the desired output for multi-input NAND gate. Okay. So remember, for PMOS, parallel, and NMOS in series. Good. Now let's look at what if we have to draw a layout. Okay. So you might have used the magic circuit layout or other tools which are typically used at university. They are open source for developing or learning the layout. Now here I'm just discussing the basic example of a layout. It may not be 100% accurate based on technology rules and all, but to understand the concept, this should be good enough. Okay, you could practice doing layout of an AND gate, NAND gate, inverter, XOR gate, or complex logic gates with magic circuit layout open source tool, or some other open source tool which your professor has advised you. All right, so let's look at the NAND gate, two input NAND gate, how we can draw the physical layout. This is the circuit. We just discussed that. We arrived at this circuit, pull-up network and pull-down network, and now let's look at the layout. So we have connected one of the terminal, okay, of the PMOS to VDD, and NMOS are connected in series, and then one terminal only of the NMOS in series is connected to ground. Okay, and both the gate of the NMOS and PMOS are connected to inputs. Good, inputs I1 and I2. Okay, and desired function of this combinatorial logic or two input NAND gate is we take from the joint of the where the pull up and pull down networks are connected together. Good. So let's draw first VDD and ground. Okay, VDD and ground we draw first. Now let's draw PMOS. Okay, so you might be aware of that the polysilicon layer passes through the another layer, and you get here in between the contacts, two contacts, you get a PMOS. Okay, and then we are going to be drawing layout for another PMOS in parallel. So this is the simple layout of two PMOS structures in parallel. Remember that since we made this contact in between, so this is saying that the first PMOS and the other PMOS, they both are in parallel. Okay, good. Now let's draw the NMOS in series. Similarly, we could draw NMOS contact and two contacts polysilicon layer, right, making the gate. Okay, red polysilicon layer representing the gate. Now notice here that when we are doing in series, we do not have any contact in between. If we put a contact here in between these two red color rectangles on green line, that will make it parallel. So we are not making it parallel here. This is a series. Okay, in PMOS we made it parallel. This was a contact, okay, in between two red polysilicon layer lines. Okay, or you can call it rectangle. Important here is not terminology or name what you call it. Important here to understand the concept that in NMOS, when they are in series, there is no contact in between. In PMOS, when they are in parallel, there is a contact in between. Okay, now let's connect it further. Okay, so both the gates of the PMOS and NMOS are connected together. Okay, and now let's connect the outputs of the pull-up network output will be taken from this contact, and then the metal layer, and then the pull down will be taken from this contact connected with the metal layer. Okay, and that is the uh, joint intersection point of the pull up network and pull down network. Good. Or in other words, the polysilicon or red lines which are connecting or making the gate of transistor, we can call it I1 and I2 inputs, okay, as if they are I1 and I2 inputs. And this output which we are taking from the intersectional joint is the desired output of the NAND gate. All right. Thank you very much. I hope you guys have you guys like this lecture. Let me know. Please leave your feedback, comments, like, subscribe. If you like the lecture, share with your friends or whomever likes to learn. Leave me your comments, and if you like to know or like me to do some other lecture on other concepts, let me know in the comment section below. Thank you very much.